Okay, today we're going to have a look at projectile motion. Now, projectile motion is a topic in Extension 1 Math, which is an extension of our calculus topic and also an extension, more importantly, of our vectors topic. So projectile motion obviously describes the motion of particles or balls or any type of projectile that's been fired or kicked or thrown out of something. So it's quite obvious to see that if you throw something, it's going to follow some sort of parabolic arc or curve. So the diagram below shows the sort of path that we would expect a projectile to move in. The two-dimensional space in which it moves has been made into a number plane, and by choosing the origin, in which case where the projectile was fired, and measuring horizontal x and vertical distance y from the origin, we can use this fact to deduce equations that model the motion of our projectiles, and they model them quite accurately. So we can express our equations of motions of projectile in a number of different ways, and in this course we're going to learn of 3 different ways to express them. Number 1, which is my favourite, is the parameterized form. The parameterized form gives you equations for the x, distance, velocity and acceleration, or displacement I should say, as well as the y, displacement, velocity and acceleration. The advantage and why I like the parameterized form is it allows you to work with 2 different dimensions at 2 different times, and it makes it easier in terms of the maths. You can work in vector form, which is just pulling those together and saying these ones are in the I direction and these ones are in the j direction. But often when you are given vector form, it's easier just to parameterize it and work it in individual dimensions. Last one, which we're going to learn more in the next video, but it's the Cartesian form. If we have a look at these 2 forms, they all involve some sort of parameter t. But we can eliminate this variable t to get what we call a Cartesian equation. And this Cartesian equation no longer has a variable t, it just has variables x and y. Okay, so where do these equations come from? Anyone with a basic knowledge of science will know that there's various equations that describe motion of objects in free space. So these include v equals u plus at, s is ut plus a half at squared, and v squared is u squared plus 2as. Now these formulas do describe the motion of particles, but they don't describe them accurately in every single circumstance, especially say in extension 2, for example, when we introduce variables like friction and air resistance. So when we're forming these formulas and when we're modelling the motion of projectiles in free space, we can't ever assume any of these formulas are true. We can't. What we're going to do, and we're trying to form a convincing mathematical argument, if we assume that these formulas are true, then it's not convincing someone who you're trying to prove the motion of projectile, it's not convincing them that it's true. In mathematics, we want to make sure our arguments are convincing and that they make sense. And we can only build on 2 fundamental kind of axioms, which is things that are universally true. Number 1 is the fact that an object does not experience horizontal acceleration once it's left its source. So once I've fired the projectile, once I've kicked it or hit it, it no longer is accelerating. It has a 0 horizontal acceleration, and that's because a projectile is not a rocket, it's not a plane, it doesn't have an engine, and there's nothing that's propelling it forward. What that means as well, acceleration, not only is it an increase in speed, but an acceleration is also your decrease in speed. So what this is saying, and this is implying that an object will have a constant horizontal speed once it's left its source. Now we know that this is not actually true because an object does experience air resistance and there's other forces that can be acting upon a particle, but in this course we will not focus on that. In extension 2 we will. Number 2 though is the fact that an object will always experience a downward acceleration of 9.8 meters per second. That's what we should be familiar with that from science and physics, that's our acceleration due to gravity. We know that all objects moving in free space are always acted upon by a downward acceleration, which is 9.8 meters per second. Now, This is universally true anywhere on Earth. It does differ a tiny bit depending on whether you're at the top or the equator of Earth, but realistically we don't care about that. And often we just approximate it to be 10. Because of this, we're going to start with y double dot is minus 9.8. Okay. So the resolution of velocity is a skill that we need to have. So as stated above, we can only work with displacement, velocity, and acceleration in an individual dimension. So due to this, it's necessary to resolve an object's velocity into its x dot, its x component, and y dot, its y component. Now, something important to note is that the angle of inclination is always with the positive x-axis. So let's resolve an object that's been fired at 60 degrees to the horizontal, which always means the positive horizontal, at 12 meters per second. So 12 is here, and 60 degrees is there. We're going to have our x dot here and our y dot here. Now that just means, obviously, that x dot is going to be 12 cos 60, and y dot is 12 sine 60. Now cos of 60 is a half, so this is 6, and this one, sine of 60, is root 3 on 2, so this is going to be 6 root 3 meters per second. Now I've got a negative angle. That just means you're going the opposite direction. Now in our motion of projectiles, our angle is generally an acute angle, and it's usually never an angle that's, say, 300 degrees. We would rather say negative 60 degrees instead of 300 degrees. So that just means it's going down that way. 60 degrees is there, 12 meters per second is there. Now this is going to mean x dot, it's still going to be 6 meters per second, 12 cos 60, and y dot is still going to be 6 root 3 meters per second, 12 sine 60, but it's going down, so this is going to be a negative velocity. So we're going downwards. Part D, 150 degrees. Well, that obviously is going that direction at 12 meters per second. And that means that this is 150 degrees, which means in our little triangle here, we're going to have 180 minus 150, which is 30 degrees. Now that means our x dot, I'm not going to consider whether it's positive or negative at the moment, but that means our x dot is going to be 12 cos 30. Now cos of 30 is root 3 on 2, so this is going to be 6 root 3 meters per second. And y dot is going to be 12 sine 60. Now sine 60 is a half, so this is 6 meters per second. But not only is this particle or object is going up, but it's going up in the negative x direction. So we need to put a minus there. Okay. Remember, velocity is a vector quantity, and speed is a scalar quantity. So velocity has not only a magnitude, but also a direction. Speed doesn't. But if it asks for speed and angle, really it's asking for its velocity. But we need to know its speed, which doesn't have a positive or negative, it's always positive, and the angle will then tell us what direction it's going. So we just need to find the magnitude of this vector, so that's going to be 5, and then we're going to say tan of theta, always, I'm pretty sure always, y on x, so 3 over 4, so theta is tan inverse of 3 on 4, which is, make sure you're in degrees, tan inverse of 3 on 4, which is approximately 36 degrees, 52 minutes. Okay, x dot is 5, y dot is minus 2. So this is now in our parameterized form. This is in a vector form in part A. So the magnitude of that vector, we're looking at the magnitude of the vector 5i minus 2j. The magnitude is going to be the square root of 5 squared plus 2 squared, or plus minus 2 all squared, which is positive 4, so root 29. And we're going to say tan of theta is y on x, so 2 on 5. So theta is tan inverse of 2 on 5, which is 21 degrees, 48 minutes. But this projectile is going down, it's got a negative y velocity, so we're going to put a negative on that there. Okay, pulling all of this together. So to answer projectile motion questions, we can never assume any of the equations of motions that you might have particularly learnt in physics. We can't assume them. We're going to forget they ever exist. They are going to pop in and you are going to be able to derive them, but we can't assume they exist unless we're told that we can assume in the question, which we often are. So a ball is thrown at a speed of 40 meters per second at an angle of inclination of 30 degrees from the top of a stand, which is 25 meters above the ground. And we're going to assume the acceleration due to gravity is 10. We're going to pull all this together to find the 6 equations of motion. Now the first thing I like to do is draw a diagram. So we're on a 25 meter high stand and we are throwing a ball at an angle of 30 degrees at 40 meters per second. So it's going to go like that and then come down. Probably not that dramatic, but it's going to look something like that. We're going to find the 6 equations of motions. To do this, we're going to individually work in either dimension. So in the x direction, we're going to start with the fact that x double dot is always equal to 0 and y double dot is equal to minus 10. So that's the acceleration due to gravity, is minus 10. And we're going to have developed our first lot of equations, which are acceleration. We're going to have a go at integrating both of these to get formulas for our velocity. So if we integrate both sides, so we're going to realise that acceleration is another way of saying the 2x to t squared. The reason that's useful is because it tells us that the right-hand side of this is we're integrating with respect to time. So x double dot is equal to 0. If we integrate both sides, we're going to get x dot is equal to some constant c. If we integrate on the other side, y dot is going to be minus 10t plus some unknown constant c. Now, we might want to, because we can't just say, oh, c, it's some constant, we don't know what it is. We do know what it is. We're going to use our initial conditions. And to do that, we're going to resolve our initial velocity, which often we give the symbol u for initial velocity, so ux and uy. So ux, of course, is going to be 40 cos 30. Now, cos of 30 is a half, so it's going to be 20 root 3 meters per second. And this one's going to be 20 meters per second. 40 sine 30. So we're going to sub in our initial conditions. When t is equal to 0, x, or initial velocity, x dot, is 20 root 3. So that means that constant's 20 root 3. So x dot is 20 root 3. Substituting in over here, when t is equal to 0, y dot is equal to 20. So that means that constant there is going to be 20. So y dot is minus 10t plus 20. Now, while you don't have to show maybe you're working to find c, it is important that you state that those initial conditions, and then it's obvious that that's what c is. Let's integrate again. So integrate that. We're going to get 20 root 3t plus c. And y is going to equal, if we integrate minus 10t, we're going to get minus 5t squared plus 20t plus c. Now this object, we're going to say, okay, it starts initially here. We're going to say it starts at the point 0 and it's up 25. So it's starting at the point 0, 25, which means when t equals 0, x is equal to 0. So that actually means that that plus c is 0. So x is 20 root 3t. If we don't need to integrate the other side again, we already have, but when t is equal to 0, y is equal to 25. So that means that c, because all of this just becomes, all of this becomes 0, so that means that constant c is 25. So y is minus 5t squared plus 20t plus 25. Now we've just formed 6 equations of motion, 3 in the x direction and 3 in the y direction, and we're going to use these to answer some questions. So part B says, find how long it rises, how long it takes to get there, What is its speed then, and how far horizontally is it from the stand? So if I'm an object and it's going up and up and up and up, we know that we have a constant horizontal velocity, which means its velocity in the horizontal direction is never changing, it's constant. In this question, it's 20 root 3. But for an object to be moving up and down, its y velocity has to be changing, and that's because gravity is influencing it. So as it's going up, the velocity is getting closer to 0 because it's slowing down, and for an object to turn around and go back down to the ground, it has to, at some point, have a 0 y velocity. So how high it rises is going to be the point at time when y dot equals 0. Now our equation for y dot is minus 10t plus 20. Now when that's equal to 0, of course, we're going to get t is equal to 2. So that is how long it takes to rise that far. Now we're going to use our equation for our height, minus 5t squared plus 20t plus 25, to actually find how high it's going. So minus 5 times 2 squared plus 20 times 2 plus 25. And we get 45 meters. We want to know its speed at this point. So its speed, well, we've already said it has a y speed of 0. So the only part of the speed we have left is its horizontal speed, and that's just a constant. So that's max height, time of max flight. Time of max height, sorry. We want to know its speed then. So its speed, the speed is just going to be its x speed because it doesn't have a y speed, which is 20 root 3 meters per second. That's that constant y velocity. And how far it is horizontally from the stand? Well, our formula for displacement in this instance is 20 root 3 t. Let's have a look at that. 20 root 3 t. So that's telling me at some point t in time, I'm 20 root 3 units away from the origin. So at my max height, I'm 2 seconds from when I started. So 20 root 3 times 2 is 40 root 3 meters. So that's how far I am from where I started. We're going to say this is our speed, and this is distance from start. Okay. Part C says find its time of flight, horizontal range, and the impact speed and angle. Now we know the equation for y is minus 5t squared plus 20t plus 25. Now the only way that we can find its time of flight is we're going to ask ourselves, well, when does it land? And it lands because, well, when you land, you're not moving anymore, you're stationary. So the second you land, that's your time of flight. Now, that's, of course, is going to be when your y is 0, because you're now down on the ground when y is 0. If we make that equal to 0, we might divide everything by negative 5. Of course, that's going to get us t is equal to 1, or minus 1, and 5. So therefore, time of flight is 5 seconds. The horizontal range, well, it's just going to be x is 20 root 3 times by time. So 20 root 3 times 5. Horizontal range always is your constant x velocity times time. It's always that instance, at least in extension 1, which is 100 root 3. So that's my range. The impact speed, I might add another page in. Impact speed. So we know, for example, in the x direction, its speed is just always going to be 20 root 3. That never changes. Our y dot, though, was minus 10t plus 20, I'm pretty sure. Let's check. Yep. And our time of flight is 5 seconds. So its y speed is going to be minus 5 times 5 plus 20, which is minus 30 meters per second. So what this is telling me is that when I land, I'm going this fast in the x direction and that fast in the y direction. We want to know that angle as well, but let's find my velocity here. It's going to be the square root of 20 root 3 squared plus 30 squared, which is 45.9 meters per second. And my theta is going to be tan inverse of 30 on 20 root 3, which is about 41 degrees. But it's going down, so negative 41 degrees. So there I've got my, what's that there, my landing speed, or impact speed. And this is my angle. Okay, let's have a look at the next example. I'm going to skip that one. We're going to go down to here. So example number 5. A particle is projected from the origin with an initial speed of 20 root 2. On its flight, it passes through the point 20, 15 at time t. Let theta be the angle of projection. Show that root 2t cos theta is 1 and 4 root 2t sine theta minus t squared is equal to 3. When we're doing these questions, if we're not given the equations of motion, what we're going to do is just find my 6 equations of motion. So we can't really resolve our velocity because we don't know an angle, but we can do it a bit generally. So we could say that it's 20 root 2 cos theta, of course, for x dot, and 20 root 2 sine theta for y dot. That's as much as we can do. Let's start. So in our x direction and our y direction. So we're always going to start with x double dot is equal to 0 and y double dot is equal to minus 10. Now you're welcome to work in one dimension at a time. I'm more comfortable, and I know you all have the ability to just work one step at a time in both dimensions, and it's a lot faster and, in my opinion, a bit easier. But do what you like. Let's integrate both sides. So x dot is going to equal some constant c, and y dot is going to equal minus 10t plus c. Now let's apply our initial conditions. This is different from the previous example because this projectile, this particle, is starting at the origin, which means that when t is equal to 0, x dot, in this instance, sorry, not equal to 0, that's our next step, but x dot initially, our initial x velocity, x dot is 20 root 2 cos theta. So my initial velocity is 20 root 2 cos theta, so my constant is 20 root 3 cos theta. Now over here, when t equals 0, my initial y velocity is 20 root 2. Why did that change to a root 3? I'm not sure. That's a root 2. 20 root 2 sine theta, which means c is 20 root 2 sine theta. So y dot is equal to minus 10t plus 20 root 2 sine theta. Let's integrate once more. So x is going to equal 20 root 2 cos theta t, and y is going to equal minus 5t squared plus 20 root 2 sine theta t. Please don't accidentally integrate sine theta and cos theta. We don't know these angles, but we're not integrating with respect to theta. We're integrating with respect to time, and that's because these angles in these questions we can find, and that just makes cos and sine theta numbers, which we can't integrate numbers with respect to theta. It doesn't make sense because they're numbers. We need to have our plus c's. Now this is actually starting at the origin. So when x is 0, or t is 0, x is 0. And when t is equal to 0, y is equal to 0. Okay. So that means our c's are both 0. So x is equal to 20 root 2 cos theta t, and y is equal to minus 5t squared plus 20 root 2 sine theta t. Okay, now we really haven't actually started the question. So we've developed our equations, and often it might take a couple minutes to actually get ready to answer the question. Sometimes in the HSC they will give you the equations and you can work with them, but sometimes you're not and you have to prove them. Now we're told that the flight, it passes through the point 2015, and we have to show that root 2t cos theta is 1 and root 2t sine theta minus t squared is 3. So it passes through the point 2015. I reckon let's substitute that into there and that one into there. So 20 is equal to 20 root 2 cos theta t, which means, divide by 20, we're done. So root 2 cos theta t is equal to 1. That's what we wanted to prove. Over here, we're going to have 15 is equal to minus 5t squared plus 20 root 2 sine theta t. Now let's look at where we're trying to go. We did have a t squared, we've got a 4 root 2. I reckon we divide everything by 5, so 3 is equal to minus 5t squared plus 4 root 2 sine theta t. And we plus everything over, yep, nice and easy. So we're going to have, oh no, actually done. We divide everything by 5 though, and that goes away. And yep, that's what we wanted to prove, nice. Okay. Part B, hence show that tan squared theta minus 8 tan theta is equal to 7. Okay. Now, we might notice that in this equation there is no t, there's only thetas. And we've got two equations that have thetas and t's. So, two equations in two unknowns. Let's make t the subject of one of these and solve. That will get rid of our t's and we hopefully will get to what we want to prove. So let's substitute that into 3 is equal to minus t squared plus 4 root 2 sine t. So 3 is equal to minus 1 on root 2 cos theta all squared plus 4 root 2 sine theta times by 1 on root 2 cos theta. Can do some cute cancelling. That cancels, that cancels. Sine on cos is tan. So this is 3 over minus 1 over root 2 squared is 2. 2 cos squared plus 4 tan theta. Right. We know that 1 on cos squared is sec squared, so this is 3 is equal to minus a half sec squared theta plus 4 tan theta. Now I'm not liking a half, and we don't see a half anywhere in what we're trying to prove, so let's times everything by 2. And I'm not liking that negative sec squared theta, so I reckon we plus everything over to the other side. Sec squared theta plus or minus 4 tan theta plus 6 equals 0. Now we're thinking, uh-oh, we're not quite there, but let's realise sec squared is 1 plus tan squared. So this is 1 plus tan squared theta minus 4 tan theta plus 6 equals 0. And we're done. That's tan squared theta minus 4 tan theta plus 7 equals 0. QED. Okay, part C I'm pretty sure is very easy. Find the two possible values of theta. So we just need to solve this equation. So tan theta is going to equal 4. Actually, I made a little mistake, sorry. When I times everything by 2, that should have become an 8. 8, 8, 8, 8, 8. Okay, so it's going to be now 8 plus or minus. Now 8 squared minus 4 times 7 is 36. Square root that we get 6 over 2. So 8 plus 6 on 2 we get 7 or 1. So we go, okay, what's inverse tan of 7? Tan inverse of 7 is 81 degrees, 52 minutes. Or tan inverse of 1 we know is 45 degrees. Okay, thank you. That's an introduction to projectile motion.